Hello, everyone. Good morning, good afternoon, and good evening, wherever you might be joining us from. I have the pleasure of welcoming you today to our webinar. I am Ashish Darbari, and I'll be talking about automatic end-to-end formal verification of RISC-V processors. So here's a roadmap for the talk. I would like to share a little bit about who we are, and then talk about processor verification challenges with simulation-based verification, why we want to actually build a formal verification solution, what are we going to do with automated formal verification solution for processors, why is architectural formal verification hard, and then I would like to describe a solution that we have built and deployed it in the field, and it exploits coverage heavily. So I'll go deep dive into methodology and results. So I am founder and CEO of Aximize. I founded this company 3 years ago, and I'm very proud to say I'm a global citizen, studied and worked in 3 continents and 5 countries. Prior to starting Aximize, I was heading the product team at OneSpin Solutions. Before that, I was heading the AVM group at Imagination Technologies. You may have come across that. And before that, I was in Bangalore for a year working for General Motors in their R&D division. I was also at ARM some years ago and also at Intel. So I do have a rather dubious distinction of having worked with all kinds of processor architectures. I have got another dubious distinction of holding a PhD with the focus on formal verification. In Oxford, they call it a DPhil. And I was also a visiting professor at University of Southampton between 2015 to 2018. My last 2 decades of life have been fully devoted on the 3 pillars of formal verification: theorem proving, property checking, and equivalence checking. Got publications and patents. So what is the vision for Aximize? We want to enable predictable formal verification for all. We want to make everyone adept with formal so they can avoid bugs, detect bugs, erase bugs for good, and prove that there are no bugs. So at the end, they can tape out silicon without any bugs. So what is the product portfolio? Obviously, we are making formal normal through a combination of different things. So we are excited about training engineers on the ground. So we have different levels of training, starting from a 1-day program to a 4-day program. It's instructor-led face-to-face or online. These days, everything is online. I'm the one who actually teaches this course, and it is delivered in different flavors, from a primer course all the way to a comprehensive course, fully methodology focused, problem solving oriented, and it's completely tool independent. So what I'm teaching here is, how do you solve problems in the field? How do you take my lab modules and apply them to projects? And the art of going big, and how do you actually cope with risks? How do you trade off time, quality? How do you apply abstractions? How do you hit exhaustive formal verification goals? And in the consulting phase, we are focusing on following up on training activities or otherwise, and advising and helping our customers build the solutions themselves. Whereas in services, we actually take up projects in the turnkey manner, and then everything from verification to strategy to planning to execution to sign off is the remit in the services side. And it works in a completely agile mode. We're very flexible. We work with customers on their requirements, providing them weekly updates. And the most exciting thing, which is the focus of today's talk, is our in-house apps that we're building towards targeting problems, I must say. And one of them is focused fully on RISC-V at the moment. And we've built a tool vendor independent, push button, easy to set up solution, which is the topic of today's talk. And we're looking at targeting architectural and microarchitectural bugs, and looking at the full spectrum of verification, from functional verification to safety, security, and power. For us, these are not just words. They mean something to us in the formal space. And the idea is to either find the bugs or prove that they don't exist. So the emphasis is very much on exhaustive formal verification. Okay, so we have happy customers, and we have happy customers in all sorts of things. So we have happy customers in training, and we've delivered services, and we have also deployed our RISC-V solution in the field. And you can read more testimonials on our website and find out. One of the things we are very excited about is sharing knowledge in the open space, and we are busy doing podcasts, often on a weekly basis, and they're available on YouTube, Apple Podcast, Amazon Alexa, you name it, Spotify, Google Podcast, Instagram. We're even on Instagram, so you can imagine the excitement we have. And if you look at the dashboard on YouTube, you'll find all of the podcasts we've been delivering. So our very last one was on visible and invisible formal verification. I think it went out about last week, I think. And I think it's already gathered 5,000 views on YouTube alone. So let's talk about processors. So why is processor verification hard, and what can go wrong? Is it even hard? So you have to look at the envelope of all of the different architectures and the different organizations building these processors. So look at Intel, look at IBM, look at AMD, look at ARM, all of the traditional powerhouses of microprocessor, and ask them, is processor verification hard? And I'll tell you every single one of them would say it is challenging. They invest a lot in verification, and this is why these processors get then into silicon, and hopefully they continue to work without many bugs in the field. But things do get wrong, right? So cores are complex, and they're massively optimized for pipelining, performance, interlocking, forwarding, branches, jumps, exception handling, stall interrupts, debug, extensions, clock gating, arithmetic, power safety, and security. In the context of RISC-V, extensions are of special interest because the RISC-V instruction set architecture is open, and it allows anyone to go ahead and build extensions to it and go and do whatever they like in their implementation, which means a lot of freedom and a lot of excitement for the designers, but sadly a lot of pain for verification people. Because not only have they got to go and verify that those extensions are correct, but they also have to ensure that they haven't broken anything else in the design. So the thing that is tricky in processors, especially in modern processors, is there's a lot going on. There's a lot of complex control, relatively short parallel paths, and sometimes you've got long serial paths, especially when you've got missed branches and so on. And you've got interleaving going on, you've got speculative execution going on, then you have interrupting the regular flow. You could have a stall because the memory hasn't returned the data back to the core. The whole core behavior, not even talking about the SoC in which it sits, is actually quite non-deterministic, and it's not easy to actually get it right. So if we were using dynamic simulation, I believe it's not adequate because you really cannot say how many simulation cycles will you run for your next sign-off. Too many dependencies and scenarios to cover exhaustively. Now, if you go back in time 3 decades ago when processors were still being built, but there was no constrained random, formal was not even alive in the way it is today, what were people doing then? They were applying directed testing. Okay, so basically architectural testing. They would go and say, okay, what happens if we actually run a subtraction instruction? What happens if we run an add instruction on a specific set of operands? What do we get? And they are great ways of bringing up a new design because you can see whether an add or a sub is actually working the way it is intended to be. But the problem is, as soon as you start looking at combinations of instructions, interleavings, and so on, this is where it gets really tricky. So for example, if forwarding is something we have built in the processor, we would like to check if it's actually working correctly. But how many combinations of forwarding? How many combinations of instruction interleaving in forwarding versus the operand dependencies in forwarding? And we just don't know, right? Because all instructions are not doing the same thing. Some are register type instructions, some are doing immediate addressing, some are load and store memory type instructions. So some are like jumps. So because instructions are not exactly the same, it's not sufficient to only pick a handful of these and just throw them out there and say, okay, we can check for sample instruction space or operand space. So it's good for bringing up, but you cannot actually sign off. So we believe simulation-based verification is non-exhaustive. I don't think you disagree with me on that one. And the main reason it is so is because it relies on input sequences and stimuluses to drive the underlying designs. And the strength of constrained random simulation is in randomization, which is great, but sadly it isn't actually enough to find all the corner cases bugs. So for example, if you look at model checking, which actually is one of the flavors in which formal verification is heavily adopted in industry, it actually exploits a systematic state space exploration technique whereby we are actually expanding the search diameter every clock cycle to cover all of the states that are reachable at that iteration. So the chances of missing bugs is much less, and in fact finding them earlier is much higher, because we are actually working with properties, but with each property we are examining the whole cone of influence that is linked into the property, which means all of the states that are interacting with each other. So whereas with randomization, you're relying more on the luck factor of trying to hit some of these states, with formal, it is extremely systematic. And this is one of the requirements. For example, if you were building a processor for automotive, is finding systematic design bugs, mandatory requirement, right? So we believe that formal verification is ready to be used for all kinds of processor verification. And for in-order processors, exhaustive verification is a walk in the park. Okay, when we are actually not doing RISC-V processor verification, for example, I want to just show you the power of formal. We threw formal at verifying design with billions of gates, okay? And here is an example of a parameterized NOC that we adapted in-house, and we worked out different configurations of these. And in one particular configuration, we had 338 million flops with 1.1 billion gates. And it took Jasper Gold 100 seconds to find bugs. Now, don't ask me how long it took me to compile this design and how much RAM I had to throw to compile this thing. But this is big, okay? This is functional verification at a design of 1.1 billion gates, okay? I haven't come across very many project teams in the world who are doing this level of formal verification. So formal is ready, we are ready, okay? Let's talk about why simulation is hard. This is ZeroRiskKey, a two-stage pipeline processor developed by the Pearl platform team. Great processors are being built by this group. And this was already in silicon when we picked up this, and it was in FPGA and in 40 nanometer ASIC. All we were trying to do was to check an architectural correctness requirement for loads, whether the load instruction works correctly. And what we found was a failure in the RTL, which was down to an incorrect operand that was selected because of the bug in the core. And one of the operands needed for the address sum, for example, was derived from an incorrect source due to the MUX being overridden incorrectly. So what was happening was they had a load instruction decode followed by some lines of code in the design where they were decoding a reg load, which is a non-RISC-V instruction. It was a custom instruction they had built for another processor, RISC-Key. And by accident, that code was left in ZeroRiskKey. What actually happened was that every time a load would be decoded, it will then encounter these lines in the code, and they would then alter the execution path, and a reg load would be issued rather than a load from memory, which basically means the load from memory wouldn't just work at all on ZeroRiskKey. Now, it may have been that when I picked up this design, this was left a few weeks before that, and maybe this doesn't exist in the silicon that they have already in the ground. I cannot say. But when we picked up the design, this is what we found. And this was confirmed as a bug. This is another example of IBEX, which was a near clone of ZeroRiskKey when it started, at least in development. And one of the lead designers who I was working with asked me to look at IBEX, and it was literally a matter of me throwing our Formalizer app onto this core, going to boil water in the kettle for a cup of tea. And by the time the water was boiled, I had already seen failures like these coming out from Jasper in this case. And the idea was that we would just orchestrate the same set of architectural properties on this new processor. And this was a bizarre corner case. So this bug was caused if an incoming debug request was sent in the core when one of the controller FSMs was in the decode state. This would then cause the processor to not execute what it was expecting to. For example, in this case, it was trying to execute a branch if equal to instruction, and it would then be thrown away, and all sets of bizarre behaviors would then go. PC will go into PC exception state. So basically, debug then overwrote anything else that should have been working correctly. Turns out that there was nothing in the design at that point which would take care of addressing it. And I did come across some code which said, we got to fix it. Now, this was because the design was going through a change phase from Zero Risky to IBEX, and the designers were working live. But this is exactly the value proposition of Formal in the way that we are deploying it in the field. It's a completely agile solution. A designer can continue to change aspects of the design, run the app, pressing a few buttons, and it can actually see failures on things that he or she may not be expecting to see. And the thing that is cute about it is that we didn't have to write any test cases or simulation sequences or anything. So whereas recreating this kind of a bug might be actually quite hard for simulation, for Formal it was, as I said, matter of having made myself a cup of tea. So why this bug was actually so hard was it was only seen when debug arrives and the controller FSM is in the decode state. It was not me believing in this. It was not me just saying this to you. We went on and proved this. We actually then went and said, okay, what happens if debug arrives, but in any other state but this particular FSM state? And it turns out the processor would continue to work correctly for all the instructions. So it would only ever malfunction if the precise timing of arrival of debug matched the state in which the controller FSM was. And it took us 7 cycles to do it. Now imagine if you were to unearth any of these bugs in the field, life would be fun, isn't it? Well, it won't really be. So why do we need an automated solution? Okay, so I love Formal, as you might have gathered by now. Absolutely love it. It's the most beautiful thing. But property checking, is easy to start but difficult to finish. Says the person who's actually been training people in the field. So I can tell you from first-hand experience, because I have seen it in action, not only in my previous jobs, but also in my lifetime of running Aximize, that in many cases, people do start well, but then they can't finish. So what is the major problem? Specifications. Let's start from there. Gathering specifications for verification is often compared to finding relevant information in a haystack. So here's what typically happens in a project. The verification guy goes to the designer and says, I'm missing some information. The designer says, okay, what information? And the verification guy says, I don't know. Of course, the designer cannot tell the verification guy what the verification guy doesn't know if the designer doesn't know what he doesn't know, right? So this is the beauty of working with people and working with the specifications that are not often fully crystallized. Now, it is not that designers don't write specifications. Of course they do. But it is often not at a level at which a formal verification guy can literally pick it up and execute it. And this process can take a lot of time. And this often is a source of missing bugs. So verification without specifications is pointless. That is one of the problems. However, finding bugs, establishing proof of bug absence and coverage is also tricky. Finding true bugs is tricky because people get spurious failures. Avoiding missing true bugs can be a real problem. Building exhaustive proofs of bug absence, everybody knows, is a hard problem because not all properties prove. For inconclusive proofs, is there a bug beyond a bound? Well, how do we know that it is or isn't? What is a coverage model that would be used for sign-off, and which one is it going to be? So if you ask Cadence, if you ask all the other vendors in the world, every vendor will tell you what they have is complete. But what is complete? And is there such a thing called absolute completeness, right? So without coverage, we can never know if we are done. So I'll talk about what we believe is the right way to approach coverage, and I'll show you how we actually make use of Jasper Gold when we're actually using that on processors. So what are we actually talking about? We're talking about building a tool, which we have, which is completely automatic, and it can achieve exhaustive formal verification results on reasonably big processor designs. So comes in our Formalizer app. It can be used to obtain proofs of bug absence. It can be used to actually simply visualize different instruction sets that people are building up, or it can be used to actually obtain a complete coverage analysis on the instruction set space towards the very end of the project, if you like. So on one end, you can start visualizing how new instructions behave, and on the other end, you can sign off with coverage completely end to end. So this is based on some new work that we've done, which is an exciting piece of work, which is how I look at it, because it can actually go down the path of looking at individual scenarios. So our automated solution end to end, what does it do? What goes in our app? Your RISC-V design, Verilog VHDL, a set of file which basically defines the mapping points between the architecturally visible design signals and our Formaliza app test bench signals, and a coverage specification if you wanted to run the coverage analyzer. If you're not interested in our coverage analyzer solution, you don't need to supply number 3. What comes out? Bugs found, or exhaustive proofs that mathematically prove under all conditions that there is no bug. Each instruction in the ISA works always as expected, not when it was the only one sent in the pipeline, but that it works correctly when it was surrounded by all of the other instructions before and after. So any of these competing requirements of different instructions trying to go after the same shared resource, any bug that can actually show up would be found. Scenarios as specified in the coverage specification can always happen. It's not the case like in functional coverage, in simulation, where we see the existence of one scenario or bins that show multiple ways of how a scenario can happen, but still finite. In formal verification space, we are proving that those scenarios of interest can always happen, and visualize that scenarios in the coverage solution can happen. So you can see a witness, an example trace, which you can then take it to a simulation engineer or a designer and show them this is exactly what's happening for the scenario of interest. So no test cases to write, no manual checker to write, and no verification code to be written. I'll talk about the scenarios later in our presentation. What kind of bugs have we found? So we verified multiple different processors, but we found tons of bugs in Zero RISC-V, in Micro RISC-V, in IBEX. And then when we threw our app on the CVE4, CV32E40P core from Open Hardware, we found issues. Not all of them were design bugs. Some of them were bugs that we found in our own test bench as well. It was more a case of matching up what the design was implementing and issues in the spec. So architectural formal verification, why is it so hard? So it's hard because of multiple actors in the field. So you have the RISC-V unprivileged ISA published by the RISC-V Foundation, RISC-V International. We have the RISC-V privileged ISA that describes the privilege instructions. Then you've got the computerized machine-readable sales specification, and this is using a formal semantics. Then you have the different microarchitecture specifications for different processors that we need to look at to align what is and isn't actually going to happen, what extensions, whether they're going to be supporting exception handling or not. Then comes the real design that we then throw against our own RISC-V ISA formal model. And all of this goes in the tool. And if there is a mismatch between what the property in our formal model is trying to check against the implementation, it could be because of any of these actors or the tool or bugs in our test bench or the design. So when we get a failure, it takes us some time to resolve whether that failure is down to a bug in the design, bug in our test bench, an anomaly in the tool, a specification aspect inside the documents that were written, or a microarchitecture specification. So this takes time, right? And details matter, and there are a lot of them. So you can go and look at these GitHubs and find out what kind of issues we have been finding. So one example of how tricky this whole business is us finding an inconsistency in the RISC-V ISA version 2.2 on page 30. What we see is this line which says for RV32I, SLLI, SRLI and SRAI generate an illegal instruction exception if the immediate 5 is not equal to 0. Of course, I went ahead and wrote a property, we threw it at the processor, and it turned out that it was failing vacuity. What vacuity means from a formal verification point of view was that actually it was not possible for any of these 3 instructions to actually have the immediate 5th not equal to 0 scenario. Because by construction, these instructions always have this bit as 0, right? So when we're trying to say, what if it is not 0, it is not even possible to build a RISC-V machine that can actually execute this specification. So this was a problem in the specification. We caught it, and there's a GitHub here. You can go and look at the interaction I had with the designers and how we finally confirmed it was an issue. So it's not like we are gurus in RISC-V architecture. We are learning aspects of RISC-V as the specification keeps on getting developed and evolved. And we're trying to reconcile all of this information, but formal is the way to go about it. But coverage is the way to ensure we are not lost, okay? So what are we talking about here? Let's get to the meat of it. So we're talking about 6 dimensions of coverage. So step 1, look at coverage targets, which is a qualitative way of doing it, easier to do it. Assertion coverage metrics, let's see what they are, get them out there. Look at the checker completeness. Look at whether we have got over constraints in formal. Look at property-driven design coverage, right? This is a beautiful way of ascertaining whether our properties, asserts, are actually doing the right thing by looking at what aspect of design code is covered by the execution of each of these properties. And a tool like Jasper Gold is fantastic at this. You can throw checkers in it, and it applies mutation, does reachability analysis, and I'll show you what the dashboards look like. And then scenario coverage is our solution that we built last summer, which goes way beyond everything else. So all dimensions are important. By no means I'm saying only one is more important than the other. But let's look at what is going on. Processor coverage targets is an easy exercise to do. And all it is trying to say is, do we have a list of all necessary assertions and covers? Do we have proofs that establish absence of bugs? All we are really saying is go and get assertion coverage list of pass and fails. Let's look at the next step. What percentage of design code is covered by our properties? This is property-driven design coverage. So we can collect that information as soon as we have a dashboard where we have results of assertions and covers. Then we want to look at, do we have checker completeness? For any given check, an assert, for example, is it verifying, checking what it needs to verify in its entirety? That is a fundamental problem that we're trying to solve in coverage. But related to this is a problem of finding out if there are any constraints that are blocking relevant stimuli. Is my check blocked from doing the right thing? Now, if you do have constraints which are bad, they can actually impact the ability of the checkers to do their job properly. So in terms of the hardness of these problems, we are now in a space where it is getting harder to ascertain whether we have over constraints, whether we have checker completeness. So are all interesting functional scenarios covered? Now, formal guys love to go back and say, hey, we have a proof that an instruction was working correctly, blah, blah, blah. Everything is great. Trust me, Jasper produced the right result. But how does a designer or a manager or an architect actually believe you that you did actually prove what you needed to prove? We need to speak a language that the rest of the world understands. This is where scenario coverage comes in. We've taken inspiration from the way functional coverage works in simulation, where it works with a functional coverage spec, and then a cover group analyzes all the interactions and then shows you the scenarios in which a tool and a simulator is actually producing examples of some scenarios reachable or not. We have taken inspiration and we've turned this into a formal verification problem where we actually read a scenario spec, coverage specification, and we automatically synthesize these scenarios for you. So then you can easily bring out these waveforms and proofs that they actually always work and take it back to the designers and the architects and this have a nice, decent discussion without them having to know all of the background of formal verification. So processor coverage targets, as I said, derive from requirements. For example, where do properties come from, right? So they come from the RISC-V ISA specification in case you're focusing on architectural formal verification. And we do build a nice plan. This is guided by ISA specification. So in the case of the open hardware, we had a spreadsheet type structure, which then got transformed into execution results. And we had tons of properties, I think 27,000 properties that got dumped into a log. But do we have enough checks, right? How do we know? Well, we believe we have, yes. And how do we go about doing this is we scan the entire specification. So when we were looking at exception handling, we looked at the word exception appears 152 times in privileged ISA and 87 times in unprivileged ISA. And what happens is in many cases, architecture mandates one thing and implementation may choose something else. And we have to scrutinize these differences so we can generate the correct exception handling checks. For example, in the case of exception handling, timing is never defined anywhere, right? So the task gets even more tedious. So this is an example of the spec on the left-hand side is what the microarchitecture specification was talking about. And this is what the architectural specification says. So we had to go and then we have to focus on each instruction and its prefix and its suffix and say, okay, when can an exception go in flight? Can it actually affect the execution of these instructions? Is exception being generated correctly? And is it because there was an exception before the jump in link instruction, for example? If an exception isn't actually going to be generated, we have to prove that it never gets generated, right? So for example, if a processor in case of CV32E40P supports misaligned loads and stores, we have to prove that those misaligned loads and stores do not generate those exceptions. So we went about proving that they don't in response to every load and store in the CV32E40P processor. And we were also able to prove for how long these exceptions would not be generated. And if they were generated, what were the root cause instructions that caused them to be generated. So that is the level of detail we are playing this game at. So coverage targets for processor verification can be obtained. For example, we're interested in deadlocks. Can we get stuck in states? Can illegal instruction signal, when a processor decodes an instruction and classifies them as an illegal instruction, is it really an illegal instruction? So we have checks for that. Register coverage for user-specified instructions proves that every instruction can decode any register between 0 and 31, but no more. And it can do this for all instructions, not just a handful. All CSR registers are accessible via CSR instructions and no more. The instruction side, at the data side, memories, caches, etc. are accessible to enough range. In cases of decoder, we wanted to see hotbed of bugs, right? All branches of decoder are exercised and they're done for the correct reason. When we're looking at stalls, we wanted to throw in an arbitrary number of stalls in the pipe, not just one or two. And we wanted to see that our constraints were not blocking the actual number of stalls, and that regardless of the number of stalls being thrown from the environment or generated by the processor, the instructions would still work correctly. So interrupts, exceptions in debug, we're still working on building a more refined model. Looking at all interrupts can be polled, interrupts are not blocked, they can activate WFI, just an example of things that we are focusing on. And assertion coverage. So this is the kind of dashboard that comes out of Jasper. We have thrown in all of our properties and Jasper produces results, and we use this kind of a thing to just visually examine the outcome of the results. Now, for example, for branch if equal to instruction, I'm just trying to tell you that it's not the case that we just go and verify that a branch if equal to always works correctly. We always do that. But we're also interested in understanding whether you can have back-to-back branch if equal to, and if you can't, then why can't you have that? So for example, we said, okay, can I have back-to-back BEQs? And for example, we can't. So back-to-back BEQ cover property, it failed. It cannot be sent out for execution. So we wanted to see why, and we said, okay, if the branch if equal to instruction was triggered, is it possible that in one cycle later, the internal design signal is low? And it turns out that actually it was, and that is why the pipe was unable to decode or detect the occurrence of another BEQ. And we can continue doing this kind of analysis to say, okay, 2 cycles later, it's also low, but actually 3 cycles later, the pipe is restored again and this internal signal is decoding or is set high. So we now know precisely for how long you can't have back-to-back BEQs, or for that matter, any other instruction, and when can the pipe be restored. So this is the kind of analysis that will reveal to the designers whether they were wasting clock cycles, the processor not doing anything, or the wait cycles were introduced for the right reason. So these are all examples of how you can get close to the power analysis and performance analysis of the processors. So property-driven design coverage, as I said, is what percentage of the design is covered by our checks. So here is an example of the Jasper dashboard. When we ran this analysis for 2 hours on the 4-stage pipelines CV32E40P in order core, we see that actually it does the stimuli coverage analysis where it tells you the reachability. And you can see 99.36% of our own test bench had been hit without any issues. And those little red ones that were there for a good reason. And otherwise, I can actually say, I think this one is for all the instructions. And basically, you can see how these checker coverage is reported from the dashboard. And the formal coverage is basically a sum of these two stimuli and checker coverage. So there are lots of hooks and switches, and when you orchestrate this coverage tool, you can also run mutation analysis. What is really awesome here is that we could find the low-hanging fruit about, oh, I missed that my checker was actually not able to check these aspects of the design. And was it because we were incomplete, because there was redundant code thrown in the processor that was there for the wrong reason? So all this kind of stuff could be resolved quite easily. And so this is, for example, another way of analyzing that we could have infinite number of stalls. Potentially, in this case, we said, could we actually have 500 stalling cycles between any two instructions? And we see here that we had a store half word, and then for 500 cycles, there was really nothing detected unless, and then you had an add I being decoded. So all our properties are run on the full core without any limitations on how many cycles the core can be stored. Formal tools do analyze all possible interactions between instructions, and they inject arbitrary number of stalls between instructions. So how do we know we haven't actually got bad constraints is an analysis we pay a lot of attention to. And there are lots of reasons of getting over constraints. You can have unnecessary assume properties, but they are easy to find. Bad configurations, you can catch them. Design introduced over constraints, easy to find via structural coverage. Dashboard, boom, gets you out there. Forgot to enable debug, interrupts, blocked stalls. These are all reasons that we could actually have scenarios, legal scenarios that could be prevented. But we can find them, right? It's not that hard. But bad property code, not easy to find, because as test benches become bigger, it gets more tricky to actually find these issues. Antecedent could be too tight, so we would be checking a property under a massive constraint, or the consequent may be too relaxed and we might be checking gibberish. Mapping points between architectural and microarchitectural state could also be a problem, and again, a tedious process but not hard. And the glue logic used in SVA test bench can also introduce over constraints. Hard to find, but they're issues that we nevertheless need to find. So here is an example of how do we actually find out bad constraints. So for example, our property said that if you do detect a branch if equal to in the pipe and the RS1, RS2 registers are equal, then register delay cycles later, the next state of the PC is the branch address. But it's not as simple as that, because we have to throw in an AND condition, because we are only interested in looking at valid decodes of BEQ, where the condition for validity was defined by us as a signal in test bench called aximize instravalid, which was derived by us by doing an AND of two signals in the design, by actually observing the two design signals, ID valido and is decoding O. They were coming now from the mapping file. But, we had used the instravalid to be the AND of ID valido and instra validi. The designer many months later told me he would consider these instructions to be valid, decodes if ID valido and is decoding O was high. So we got a little bit worried, thinking if we were actually misclassifying the instructions to be valid at the wrong time, or, and we had to go and then basically establish that those two conditions were equivalent in the design, and that either way we were observing the validity of a legal instruction in the correct way. So with formal, we can do this kind of analysis in a matter of seconds. Ruling out design or test bench issues is another example. So relaxing constraints is a great way of actually understanding whether or not you've over-constrained the design. So sometimes what we do is we deliberately relax the constraints, take them off, or break them to see what exactly is the design going to do. So this is a property we had on an e-brake instruction. For example, it's only one part of the check, which says that if you have an e-brake, valid e-brake instruction, then 3 cycles later, up to within 3 cycles later, the MCOS register would have this code. And it turns out that actually, it was not happening because we had blocked the memory from returning the return valid I instruction, return valid I signal, and which you can see in this waveform is held low. So what was happening was that you have an e-brake in this clock cycle, but before this e-brake, and this is the consequence that we were looking to observe in the MCOS queue, but before this e-brake instruction, there was a store instruction, and because the store instruction was expecting a handshake to go through, to allow the RValidI to handshake so that it can actually complete. And effectively, because the RValidI is low, the processor is deadlocked. So if the memory for some reason is not returning an RValidI and you have another instruction ahead of eBreak, you can have a deadlock. Now, in reality, you could say that this can happen to any instruction, and this isn't really a design bug. In my opinion, because eBreak is a higher privileged instruction, eBreak should have the priority and we should be flushing the pipe, not sitting there waiting for RValidI. Another thing to consider is my check verifying and catching the right bugs. So we employed the mutation thing with hand. So we basically said if this was a branch of equal to property, and if you have a BEQ here, the next state of the PC, which is 2 cycles later, we expect to see the branch address. And do we see it? And in fact, we do see it. But what if there is a bug that meant that the next state of the PC could be altered incorrectly in the interim cycle? So we introduced this bug by hand, and what we found there was straight away, we basically went and changed the RTL by hand, and we found that all of these properties are failing. Not only the BEQ checks, but the invariant property and the program counter also failed quite quickly, actually. So we were reassured that our checks were doing the right thing. But is this enough? All of this analysis. So we believe that exploiting scenario coverage is the right thing, because then we can go back and answer, how do we know that all instruction sequence interleavings have been verified? Someone can say, show me that you've tested all sequences, prove it that you've tested all sequences. So scenario coverage, have we covered all interesting scenarios? What are we talking about? So we're talking about creating visual evidence of seeing that actually when we verify these interleaving instruction sequences, can we get them to work correctly? Can we have visual evidence that they're working correctly, and have specific flavors of these to look at? So for example, we may be interested in looking at a data forwarding scenario of an OR instruction followed by XOR followed by AND, and we may want consecutive or non-consecutive occurrences of the prefix and the suffix instructions. So there is this concept of having an observed instruction, which is an OR instruction. In this case, we have already formally proven that OR instruction works correctly, meaning any number of repetitions of OR that were sent in flight before and after any other instruction meant that OR was working correctly for a given processor. But now we're saying, what happens if OR was preceded by a subtraction instruction two times consecutively or non-consecutively, 4 cycles after reset, and then an OR instruction was set at 5, followed by 1 cycle later an AND instruction. And this trace coming out of the coverage analyzer and in combination with Jasper Gold shows that actually this is a scenario that is possible for this particular instruction in the pipe. And we can create multiple instances of instruction interleavings simply from a spreadsheet entry that the user specifies. So how many scenarios to analyze for a processor? Well, quite a large number of scenarios really, but we can't actually do justice to this, because if you consider permutations of 40 user instructions, let's say, and then privilege instructions, and you look at the space of all possible permutations, it's a huge space. So what we're looking to do is either to work with the designer's coverage spec or ask the architect designer to see which scenarios you were interested in, or if they were not accessible to us, then we would generate a scenario spreadsheet like this, where we would give each instruction a chance to be interleaved with an arbitrary prefix and a suffix. And then we will throw this in the app, leave it running, and out comes the results. And Jasper Gold will show us that for each scenario of interest, the synthesized properties marked as row entries can be mapped down to spreadsheet. We have the right properties, and that they do proof showing that those scenarios would always work correctly. The corresponding covers would generate the visualization waveforms. So coverage-driven end-to-end formal verification for RISC-V is a reality that exists today in the form of our Formalizer app running on top of Jasper Gold. And what we're talking about here is a summary. We've got a coverage-based solution which is fully automated. It's industry's first and only end-to-end vendor-neutral formal verification solution. It works nicely with Jasper Gold, works with other tools as well. We have spent the time creating the efficient properties. We've spent the time creating coverage targets and doing all this analysis. You can benefit from it out of the box and run with it. And at that point, thank you very much for your interest, and I'll be happy to stop and take questions for you. Thank you very much.